In this video, we're going to explore how a buffer changes its pH with the addition of a strong base. In this case, we're going to use a propanoic acid solution. I have 0.55 molar propanoic acid, and I'm going to have 0.075 molar of its deprotonated anion. This is in a 1 liter container, and it makes our buffer. We then are going to add 5.3 grams of potassium hydroxide to this bottle. What we want to know is how much does the pH change by? Well, to know how much it changes by, we need to know what it was to start with. So let's find the pH before the addition. Well, in that case, I've got my Ka. It's going to equal my H+, my base, propanoate, and my acid, propanoic acid. We want to solve for H+, so we're going to rearrange. We'll multiply our acid up. We'll divide our base down, and all that will be equal to the H+. Our acid, 0.55. Our base, 0.075. And our Ka, well, I don't have that right away, but I do have pKa, which 10 to the negative pKa will be the Ka, so 10 to the negative 4.89. All that has to equal our H+. Multiply that out. What was our original H+, and thus what was its pH? Original H+ was 9.4 times 10 to the minus 5, giving the original pH of 4.0247. Additionally, we could have calculated this using the Henderson-Hasselbalch equation. Our pH was equal to the pKa plus the log of the base over the acid. 4.89 plus log 0.075 divided by 0.55. We'll find the same thing. The pH would equal 4.025. A little rounding error. Basically, we get the same answer. Same calculation, we'll get the same answer. This was our initial pH. Well, we're going to add sodium hydroxide, specifically 5.3 grams of it. Well, we know the original amounts of our starting materials. I've got a molarity and I've got a volume, so I can find the moles for them. For the propanoic acid, breaking into H+, propanoate, initially we'll have 0.55 mole. We'll assume no reaction occurs yet, so no H+ yet, and 0.075 mole of my weak conjugate base. What's going to happen is I'm going to add that hydroxide. Well, potassium hydroxide is going to break into K+ and OH-. It's a strong base. That OH-, we're suddenly going to have a lot of it in solution, way more than would naturally occur from our equilibrium with water. As a result, it's going to start reacting and consuming things, and, well, it sees a proton hanging out on propanoic acid. It can steal that proton. And so if I have a propanoic acid and a hydroxide comes by, it's just going to grab that H+. Result is that we will get water and a propanoate, the conjugate base. Strong base is consuming, so strong base consumes the weak acid. It's going to react with it. It's going to steal the donatable proton off of the weak acid. That's what an acid's good at doing, donating the proton. The hydroxide's strong base, it's going to accept that proton. So the weak acid gets destroyed. But what's left over after it donates that proton? Weak base is created. So strong base creates weak base. It's just the opposite of what happened with the strong acid. If you add to a buffer a strong acid or base, it's going to increase one of the weak components and decrease the other. And it always increases the like kind. A strong acid increases the weak acid. A strong base increases the weak base. So what's going to happen here is we're going to add the KOH, and we're going to lose some amount of our acid, and we're going to gain some amount of our base. How much? Well, we need to know how many moles we're working with. 5.3 grams of KOH. It's approximately 56.1 grams of KOH in 1 mole. So we're working with 0.0945 mole of KOH. That's what we have to react. That's what can attack our weak acid. So the weak acid's going to lose 0.0945 moles. In doing so, it's going to create that much weak base, and so we're going to create 0.0945 mole of the weak base. We're going to get new values out. 0.4555 mole of my weak acid will still be around after this. And 0.1695 mole of my weak base will be around after this. So our strong base changed the concentrations of our buffer components. It changed how much weak acid and weak base we had. Once we have those values, we just solve for the equilibrium concentration of the H+ ion. Ka is going to be H+ base of 0.1695. This is in 1 liter of solution, so we can put it back in 1 liter to get these concentrations. 0.4555 moles per liter. Our Ka, 10 to the minus 4.89, must equal the H+. We're going to multiply that acid up. So we'll have 0.4555 up with the Ka. We have to divide the base down to get it to the other side. 0.1695 beneath. So we've reorganized to solve for the H+. Found that our H+ is 3.46 times 10 to the minus 5. Take the negative log of that. 4.46 is our pH. So let's compare it to before we added the potassium hydroxide. It was 4.025 initially, and now it's 4.46 after. So there was a reasonable change. We altered the pH by about 0.44. 0.436. That is our change in pH. Now, if we'd simply put the potassium hydroxide into 1 liter of water, we have that many moles of potassium hydroxide, which would have become that many moles of hydroxide. And so we could have found the pH from that. POH would equal negative log of 0.0945 moles per liter. Again, this was a 1 liter solution, so our moles is our molarity. This would have been a POH of 1.024. So our pH would have been 14 minus the POH. Our pH of just the potassium hydroxide on its own would have been 12.97. Neutral water is 7. Putting this much potassium hydroxide in would have raised it to almost 13. A difference of 6 pH units, 6 orders of magnitude. Instead, we saw less than a half a pH unit. The buffer prevented wild pH changes by reacting with the hydroxide. Instead of about 0.1 moles of hydroxide floating around, they were consumed by reacting with the weak acid. Those hydroxides all went away, and the new concentrations of weak acid and base re-equilibrated to produce the H+ in solution.